Welcome back to our electric circuits series. Today, we're diving deeper into circuit analysis and problem-solving techniques with our third lesson. In our previous lessons, we established a strong understanding of fundamental electrical concepts such as voltage, current, resistance, and circuit structures. We explored complex circuit configurations like nodes, loops, branches, series, and parallel setups, as well as applied Ohm's law and understood the functions of voltage and current sources. Now, we are equipped to tackle more complex circuit analysis problems and explore more advanced circuit laws. In this tutorial, we will cover Kirchhoff's laws. These fundamental principles play a crucial role in analyzing complex electrical circuits. This is being produced in collaboration with Digilent, and we want to acknowledge Digilent's invaluable support and collaboration in previous lessons and their continued support as we go forward. So let's do a quick recap of some of the techniques we previously learned that served as valuable tools for circuit analysis. In series circuits, components are connected end to end. The total resistance is the sum of individual resistances. Current remains the same across all components. In parallel circuits, components are connected across common points. The total resistance is calculated using the reciprocal of individual resistances. Voltage remains the same across all components. Ohm's law is the relationship between voltage, V, current, I, and resistance, R. It's expressed as V equals I times R, or I equals V over R. This law helps calculate voltage, current, or resistance when two of these values are known. Now that we've refreshed our memory on these techniques, let's move on to Kirchhoff's laws. Kirchhoff's current law, or KCL, deals with current flows at junctions in a circuit based on the principle of charge conservation. So imagine a junction like a water pipe. The total water flowing in must equal the total water flowing out. Similarly, in a circuit, the total current entering a node equals the total current leaving it. Mathematically, this is represented by sigma I in equals sigma I out, where the Greek symbol sigma stands for summation. Kirchhoff's current law can also be stated as the sum of all currents entering or leaving a node in any electrical network is always equal to 0. So let's look at this with an example. In the given figure, we have a node A with currents I1, I2, and I5 entering the node, and I3 and I4 exiting the node. If we assume passive sign convention such that the currents entering the node are positive and the currents leaving the node are negative, according to KCL, the sum of the currents entering a node is equal to the sum of currents exiting it. Hence, we can see that the sum of all currents entering or exiting a node is 0. Let's work through a few examples together to better understand KCL in action. For our first example, consider this circuit with points A and B. Current I1 enters point A while I5 exits point A, while I4 enters point B and I3 and I2 exit point B. We are given that I1 equals 4 amps, I2 equals 3 amps, I3 equals 2 amps, I5 equals 1 amp, where A represents amperes. Let's find the value of the unknown branch current I4. Now, to find the value of I4 in the given circuit, we can apply KCL. Since points A and B are electrically the same point, we consider them as the same node. Again, according to KCL, the sum of currents entering a node is equal to the sum of currents leaving the node. Hence, the currents entering the node are I1 and I4, while the currents leaving are I2, I3, and I5. Applying KCL, we can equate the sum of all the currents entering the node with the sum of the currents leaving the node. I1 plus I4 equals I2 plus I3 plus I5. Then we can substitute the given values with 4 amps plus I4 equals 3 amps plus 2 amps plus 1 amp. Then we combine like terms, we have 4 amps plus I4 equals 6 amps. Isolate I4 by subtracting 4 amps from both sides gives us I4 equals 6 amps minus 4 amps, or I4 equals 2 amps. So the value of I4 in the circuit is 2 amps. In our next example, we'll use a more complex circuit. Let's consider the following setup. There are two voltage sources, V2 equals 30 volts and V3 equals 20 volts, along with three resistances. R1 equals 100 ohms, R2 equals 1000 ohms, R3 equals 150 ohms. Current I1 passes through R1, I3 flows through R3, and I2 flows through R2. Let's calculate the branch currents I1, I2, and I3. As you may observe, I1, I2, and I3 all flow through their respective resistors, meeting at node V1. We can assume that currents I1 and I3 flow into node V1 from their voltage sources V2 and V3 respectively. We can also assume that current I2 flows out of node V1 towards the ground. Hence, applying KCL at the node, I1 plus I3 equals I2. According to Ohm's law, I equals V over R. Hence, we can substitute the currents in an equation with their V over R equivalents. To find the potential difference across each resistor, we calculate the difference between the voltages at each node on either end. This potential difference divided by the resistance gives us the branch current. Substituting the values in the KCL equation, I1 plus I3 equals I2, can be written as 30 minus V1 over 100 plus 20 minus V1 over 150 equals V1 over 1000. We can simplify the equation further by reducing the denominators before eliminating them completely. At that point, it's just arithmetic, which gives us V1 equals 24.53 volts. If this isn't clear, just pause the video for a moment to make sure you follow all of these steps. Once you're confident about this, you can substitute the value of V1 in the equations for I1, I2, and I3. And we get I1 equals 0.055 amps, or 55 milliamps, I2 equals 0.025 amps, or 25 milliamps, and I3 as negative 0.03 amps, or negative 30 milliamps. So the value of I3 is a negative value. There's no reason to panic about this. It simply means that the actual direction of current flow is opposite to our initial assumed value, according to the passive sign convention, and that current I3 flows out of or exits node V1. Again, it is important to note that negative values of currents or voltages in circuit analysis indicate a direction opposite to the assumed direction, and that's all. This assumption is made based on the passive sign convention, which assumes that current flows into the positive terminal of an element and that voltage drops occur in the direction of current flow. Therefore, a negative value signifies a reversal in the assumed direction, indicating that the actual current flow or the voltage drop is in the opposite direction. Now, let's talk about Kirchhoff's voltage law, or KVL, which deals with voltage changes in a closed loop within a circuit. As you may recall, this is what a closed loop in a circuit looks like. As you traverse a loop, you encounter voltage rises from sources and voltage drops across components like resistors. Kirchhoff's voltage law states that these must add up to zero in a closed loop. In simpler terms, it emphasizes energy conservation within a circuit. Mathematically, KVL is represented by sigma V rises equals sigma V drops, where here V stands for voltage, which is the electrical potential difference across a component in the circuit. Rises refer to voltage increases across components like voltage sources, batteries, or generators, as you traverse the loop in a specific direction. These voltage increases are typically positive in the equation. Drops indicate voltage decreases across components like resistors or other loads as you move along the loop. These voltage decreases are usually considered negative in the equation. It is important to note that when you encounter a new circuit element, you need to pay attention to the voltage sign as you enter the element. If the sign is positive, it indicates a voltage drop across the element, and the element voltage must be subtracted. Conversely, if the sign is negative, it signifies a voltage rise across the element, and the element voltage must be added. This approach helps us correctly determine the voltage changes across elements in a circuit. To summarize, the sum of the voltage rises, or the positive contributions, and voltage drops, or the negative contributions, across these components must equal zero for a closed loop. Let's demonstrate KVL with an example circuit. Here, we have a simple example circuit with one loop. There is a voltage source where V equals 20 volts and three resistors in series, R1, R2, and R3. We can find out the current flowing through the circuit using the series and parallel techniques and Ohm's law that we discussed in the beginning. Since the resistors are in series, we can find the total resistance by summing up the individual resistances. R total equals R1 plus R2 plus R3, which gives us R total equal to 40 ohms. We can then find the current flowing through the circuit through Ohm's law. 20 volts over 40 ohms gives us 0.5 amps. And now that we know the value of I, we can find the voltage drop or difference across each resistor. VR1 equals 15 ohms times 0.5 amps, or 7.5 volts. VR2 is 20 ohms times 0.5 amps, giving us 10 volts. VR3 is 5 ohms times 0.5 amps, giving us 2.5 volts. As a sanity check, you can verify that the voltage drop across the three resistors adds to 20 volts. Now, let's validate Kirchhoff's voltage law using the results we have obtained from our previous calculations. In this circuit, we have one loop. As we traverse the loop clockwise, we account for voltage rises from sources and voltage drops across resistors. Applying KVL to the loop, we write Vs minus VR1 minus VR2 minus VR3 equals 0, which gives us 20 minus 7.5 minus 10 minus 2.5 equals 0. And this equation essentially means that the sum of the voltage rise from Vs minus the voltage drops across R1, R2, and R3 equals 0 in the loop. This equation illustrates the energy balance within the loop, validating Kirchhoff's voltage law. Let's look into a few more examples to better understand KVL in action. So in this first example, let's consider the following circuit with resistors R1 equals 5 ohms, and R2 equals 3 ohms, and a current source I1 that outputs 5 amps. Now we can determine the voltage drop across the current source using KVL. Since the resistors are in series, the current passing through them is the same. So according to KVL, Vs minus VR1 minus VR2 equals 0. And then we replace the voltages with the current times resistance equivalents with Vs minus I1 times R1 minus I1 times R2 equals 0. Replacing the numbers, we get Vs equals 25 volts plus 15 volts, or Vs equals 40 volts. For our second example, let's consider a given circuit with two loops. There are two voltage sources, V1 equals 5 volts and V2 equals 2 volts. Currents I1 and I2 pass through loops 1 and 2 respectively, with resistances R1 equals 2 ohms, R2 equals 3 ohms, and R3 equals 1 ohm. Using KVL, let's find currents I1 and I2. Let's look at this circuit. There are two loops with loop currents I1 and I2 passing through loop 1 and 2 respectively. Now we have an additional concern. When dealing with circuits containing two touching loops, sometimes we encounter situations where shared resistors are part of both loops. In such cases, to determine the current through the shared resistor, we subtract one loop's current from the other loop's current. This approach ensures that we account for the flow of current through the resistor from both directions in the circuit. So resistor R3 is the shared resistor between loops 1 and 2. As we can observe, current I1 passes through R3 from B to G, while current I2 passes through R3 from G to B. So we can consider that the current through the middle resistor R3 is the difference of currents I1 and I2. Using KVL to find the loop equations, we get loop 1 as 5 minus 2 times I1, minus 1 times I1 minus I2. Simplified, this comes out to be 3I1 minus I2 equals 5. Loop 2 is negative 3 times I2 plus 2, plus 1 times I1 minus I2, which simplifies to 4I2 minus I1 equals 2. So as I just mentioned, observing the sign of a new circuit element while traversing a closed loop is important. A positive sign implies a voltage drop, requiring subtraction of the element voltage, whereas a negative sign indicates a voltage rise, requiring addition of the element voltage. Thus, in loop 2, the negative sign upon entering the circuit element signifies the addition of the voltage source of 2 volts. Solving the simultaneous equations for loop 1 and loop 2, we simplify this down to 11I1 equals 22, or I1 equals 2 amps. Then we can solve for I2 and get 1 amp. Now that we know how to apply Kirchhoff's electrical circuit laws, let's discuss how we can apply these laws together to solve electric circuit problems. Here's how we go through things step by step. First, identify nodes. Second, define branches and loops. Third, apply KCL to nodes. Fourth, apply KVL to loops. And finally, fifth, verify and analyze. We begin by identifying nodes where currents converge or diverge. Label these nodes for clarity. Within the circuit, we outline the branches and loops. At each node, we apply Kirchhoff's current law to write equations representing the current balance. The sum of currents entering the node should be equal to the sum of currents exiting the node. The simultaneous equations at each node have to be solved to find the unknown currents. After that, we choose loops within the circuit and apply Kirchhoff's voltage law to write equations representing voltage rises and drops around each loop. The sum of voltage rises and voltage drops around a closed loop should be 0. These equations, along with the current equations from the previous step, can be solved to determine unknown voltages or currents. Once you've solved the equations, verify the results by checking for consistency with Ohm's law and other circuit principles. Analyze the circuit behavior based on the calculated values. Let's illustrate these steps with another example circuit and walk through the solution using Kirchhoff's laws. Consider the given circuit. Using KCL and KVL, let's find the currents through each branch of the circuit as well as the voltages across each element. Step 1 is to identify and label the nodes in the circuit. Let's call them Node A, Node B, Node C, and Node D. Here, we can also assume the current directions based on the voltage sources in the circuit. Current normally flows from the positive terminal to the negative terminal of the source, or based on passive sign convention. Step 2 is to define branches and loops. Outlining the branches, resistors or sources, and loops, closed pathways, we have 2 loops in this circuit, loop 1 and loop 2. Step 3 is to apply KCL at each node. Here, at node A, the KCL equation would be I3 equals I1 plus I2. Step 4 is to apply KVL at each loop, loop 1 and loop 2, and to write KVL equations representing voltage rises and drops. So 20 volts minus 10 times I3 for loop 1. For loop 2, we have 100 volts minus 20 times I2 minus 5 times I2 minus 10 times I3. Substituting the current equations obtained in step 4 into the loop equations and solving defined currents, we get the value of the unknown branch current. There's quite a bit of math here that will show up on the screen long enough that you can pause the video and go through the steps if you're uncertain about the math. After loop 1, we'll show loop 2 and then show the steps that will yield our results. So the math here is simple, but there are a few steps, so please be careful not to get lost in the math or, much more likely, make some sort of transcription mistake. All right, after going through all this, we find that I2 is 3.2 amps, I3 is 2 amps, and I1 is negative 1.2 amps. Again, the negative value of I1 simply means that the actual direction of current flow is opposite to the direction of current that was initially assumed. So our circuit would look more like this. I highly recommend taking a moment to look this over, make sure you understand it intuitively as well as mathematically. What is exactly going on? Then, using the results of these equations, we can determine the voltages VR1, VR2, and VR3 as 20 volts, 16 volts, and 64 volts, respectively. The last step, or the 5th step, is to verify the calculated values against Ohm's law and circuit principles to ensure consistency. Let's put the values in loop 1 to make sure that everything cancels out. 20 minus VR1 equals 0, which then becomes 20 minus 2 times 10 equals 0, so the math works with loop 1. With loop 2, it's a touch more complicated. We have 100 minus VR3 minus VR2 minus VR1 equals 0, which then, with the values we calculated, becomes 100 minus 3.2 times 20 minus 3.2 times 5 minus 2 times 10 equals 0. Which then becomes 100 minus 64 minus 16 minus 20, which equals 0, showing that the numbers fit perfectly with loop 2 as well, so we have the correct numbers. This example demonstrates the practical application of Kirchhoff's laws in analyzing complex electrical circuits. By systematically applying KCL and KVL, we can solve circuit problems efficiently. So, in summary, the exploration of Kirchhoff's laws in this 3rd lesson has enhanced our understanding of circuit analysis and problem-solving techniques. Again, we are grateful to Digilent for their continued support and collaboration in bringing these educational resources to students and enthusiasts. Their commitment to academic development and affordable solutions has been invaluable to creating this learning journey. So in future lessons, we will continue learning more circuit analysis techniques and build upon the knowledge and skills we've acquired so far. So stick around for more interesting content and to learn more. And as always, if you liked this video, give it a like, subscribe to our channel, and we will catch you in the next one. Take care. Hey, we hope you enjoyed this video. Did you know that CircuitBread.com does more than just tutorials? Besides tools, textbooks, and other things, we host an ever-growing library of math and electronics-related equations and glossary terms. Don't have the entire table of integrals or Faraday's second law memorized? We gotcha. Go check them all out.